Okay, welcome everyone. How is the volume on the speakers here? It's okay? Those in the back can hear even? Good. So hopefully you're here for the right course. This is Comp 2804. I think the course is called Discrete Structures too. So it's really about mathematics for computer science, discrete mathematics. So a couple of administrative things, and then we'll jump right into a couple of little topics to give you a flavor of what this course is about. So this is me, Pat Morin. If you need to address me, you can just call me Pat. So don't call me doctor or professor or sir or any of those things. And if you don't feel comfortable with that, because some people don't, just find a way to get my attention without saying my name. So put up your hand or catch my eye or something. That's easy to do, I know, because I'm terrible at remembering names, so I have to do it myself all the time. My office is 5177 in the Herzberg Physics Building. What else? Administrative details about the course. I guess I have to explain the grading scheme. So there will be 4 assignments in the course. In total, they will be worth 25%, and they're all equally weighted. So I guess that's 12 or 6.25% each. There will be a midterm exam, also worth 25%, and there will be a final exam worth 50%. Final exam is cumulative. It covers everything in the duration of the course. I get asked this all of the time. There's no, so this is the grading scheme, and with the exception of documented illnesses or other reasons for missing things, there's no scheme to like take the maximum of the midterm or the final exam, or the final exam overrides the midterm if you do better. This is the grading scheme. You can't blow the midterm and then somehow make it all up on the final exam. It's still worth 25%, and it will always be worth that. The only exceptions are if people are sick for one of these grading things, then the weight gets shifted onto similar ones. So if you miss one of the assignments because you were sick, then your assignments, you'll get the average of your 3 assignments instead of your 4 assignments to make up this 25%. If you miss the midterm because you were sick, there's not a make-up midterm. Everything then rides on the final exam. Okay. So in this course, you actually probably received an announcement about it already from this. There is a course webpage on CU Learn, but it's really just a skeleton of a course webpage. And what you can find there and what CU Learn will be useful for will be submitting assignments, so when you do your assignments, you will submit them as a PDF file on CU Learn. A little bit more about that later. There's also an announcements forum, which only myself and the TAs can post things on. And there's a course forum, which you guys can post things on and discuss things amongst yourselves. And know that this is also monitored lightly by me and the TAs. So we'll be monitoring that to make sure you're not doing things like posting completed solutions for assignments. But also we'll be monitoring it in case we can help you. So if you have questions about things, about course material, either on the assignments or in class, you can ask on these course forums. And the good thing about that is there are something like 385 of you. So that means that almost any time of the day, there's somebody looking at these forums, and you'll typically get answers very quickly. So there's plenty of you who are smart, and welcome the opportunity to show how smart you are, and you can do that on the course forums if people ask questions. And that's much more efficient usually for you than sending me an email with a specific question about something we did in class, because well, even if it takes me 5 minutes to answer that email, but half the people in the class send that, well, that's 200 people each using 5 minutes of my time. It's going to be a while before you get an answer to your email. And so if you ask me those kinds of things, you'll get an answer much faster on the course forum. And there's an added advantage that probably a lot of people have the same question. It gets answered once. Everybody gets to see the answer that way. And the final and most important thing you have on CU Learn is the link to the real course webpage. So the actual course webpage is hosted on a server in our research lab. And the reason for that is, well, systems like CU Learn, they're essentially paywall systems. They protect material behind a paywall that you guys have access to because you're registered for this course, you paid your tuition, but nobody else in the world has access to that stuff. And I want it to be available as broadly as possible. So it's on a real public-facing web page. Anybody can go and access the material for this course. They don't have to be registered for it. If you go to the real course web page, you'll find the outline for the course, all the information that I'm talking about today, a breakdown of the topics week by week. Now, right now, the dates attached to those topics are the dates from last semester, but we'll be doing roughly the same thing this semester, so you'll have an idea of what's coming. And you will also see a whole bunch of YouTube videos of the lectures from this course last semester, and as we progress through this semester, you'll get videos of the lectures that I'm giving now. There's our cameraman in the corner. If you are shy about appearing in videos or having your voice heard in videos, you're lucky. If you don't want to appear in them, just don't sit in the line of sight of this thing, or even if you do sit in the line of sight, just come in on time because we don't start recording until I start lecturing. So the only people typically who show up in videos are those who come in late and walk in front of the camera. And if you're worried about a question that you asked during the class being heard, don't be. They can't be heard. The sound for that camera is recorded here, this thing attached to my hip. So you ask a question, the camera is not going to pick it up, and often I will repeat the question just so the people watching the video later can know what was asked. Okay. So any questions so far? So this is a big class, but I would still like to keep it interactive, and so I will pause often and encourage people to ask questions. And sometimes I will ask you a question and wait awkwardly for up to 30 seconds for someone to answer, because I'm certain that in a class this size, someone can answer. It's just that they're kind of shy. And usually that happens because either the question is so difficult that nobody knows the answer, or almost nobody knows the answer, or the question is so easy that people just feel it's a stupid thing to answer. But in any case, sometimes we just won't move on until until somebody tries to answer. Okay. Now, there's one unpleasant piece of business that I have to cover, which is the new policy for academic violations. Again, because of the numbers in this course, I am certain that there are people here who have committed academic violations, even been caught, and maybe even interviewed with the dean before. And because of the number of these things, they've become so problematic, that much stricter policies are in place starting now, January 2020. Okay. So an academic violation is, for example, you copying someone else's assignment, more or less verbatim or without understanding it, at least. And you know, if that happens, and TAs will be marking your assignments, they often find these things. The two assignments will be packed together, documented, and sent to the dean's office to deal with. And if this is really found to be an academic violation, well, what happens differs depending on whether it's your first, second, or third violation, and there are no fourth violations. You'll soon see why. For your first violation, because all of you are now past your first year, you will receive an F in the course. Okay. So that's as far as I go, because when you receive an F in the course, then you basically don't bother coming or doing work anymore. But if this happens again in another course, then you receive a 1-year suspension from the program. Now, I'm not exactly sure how broad scale from the program means, but it certainly means from the School of Computer Science, the computer science program that you're studying. It may mean anything in science. Maybe you could go enroll in an arts degree or something for that 1 year. And the third violation is expulsion from the university. So after this happens 3 times, basically you're asked to leave the university and never come back. All right. But now that everyone knows, we don't have to worry about these particular these particular penalties, because none of you are going to commit an academic violation. Please. And a couple of little things about these assignments. Here, so this is really a course about mathematics for computer science. So assignments are done by writing up solutions to the questions that are asked on the assignment and submitting them. And the way you submit is an assignment that consists of one PDF file. So there are 2 options for making this kind of PDF file. Actually, there are many options, but 2 sort of main paths to this. One of them is to use LaTeX, the LaTeX typesetting system, typeset all your solutions really nicely, including all of your formulas and things in LaTeX, and submit that, because LaTeX easily generates PDF files. The other is to do your solutions by hand and use a scanner, but nowadays scanners are kind of almost gone. There's plenty of apps for your phones that can take pictures of pieces of paper, square them out nicely, and convert those to PDF files. Yep.
Pat, are you allowed to send photographs of your assignments?
You're allowed to send a PDF file, which can be made up by taking photographs of your assignment and having an app convert those into a PDF.
Okay, so I could handwrite these, like make it into PDF, and everyone would still be cool with that.
Yeah. So probably, I don't know, 1/2 to 3/4 of the students do them by hand and then do something to scan them. But by now, scanning is as easy as getting the right app for your phone, taking pictpictures of each page, and then exporting that as a PDF file. There is a limit on CU Learn of you can't submit a file that's bigger than 500 megabytes. That's half a gigabyte. That's an enormous file, so that you shouldn't run up against that. Okay. So that's one thing about the assignments, and there's no, you can't do anything else because CuLearn will only accept a PDF file, and it'll only accept one of them. The other thing to look out for is that deadlines are strict. And by strict, I mean to the minute. Assignment 1, for example, is due at 11:55 p.m. on a particular day. If you try and submit at 11:56 p.m., it won't be accepted. There won't even be a submit button available to you. And I, unfortunately, can't make exceptions to that. In fact, I won't even answer emails of the form, oh, it's 11:57 and I didn't submit my assignment or whatever. Just please submit on time. And there's a safety thing you can do. If you're really working on the assignment up until the last minute, then, generating a PDF file, yeah, it's easy once you've done it a few times, but if the first time you're doing it is 3 minutes before the deadline, then there's a chance that it might take you more than 3 minutes. So early on, when you've done half the assignment or 3/4 of the assignment, as long as there's lots of time left, try this. Generate the PDF file, submit it, because you can always revise it. You can always update your submission up until the deadline. So if everything goes really, really wrong and you don't get to submit your final version, you at least have submitted something with half the work or 3/4 of the work done. And that's kind of important because even if you don't care about the 6.25% that the assignment is worth, maybe you're not chasing marks that hard, you probably would like to know how you did on the assignment so that you know if you understand the material or not. And if you don't submit anything, then the TAs can't mark anything. They can't give you any feedback. All right. Any questions there? Yeah.
Would you recommend using LaTeX?
I highly recommend learning LaTeX because, well, for a lot of reasons. It's, there's a little bit of a learning curve, but it's a really useful technical skill to have as a computer scientist. So it's a wonderful typesetting system created by one of the fathers of computer science, Donald Knuth, that does a really spectacular typesetting. It's what professional publishing houses use for science and mathematics textbooks. And the other thing is the math. So LaTeX has a whole thing for setting paragraphs of text and books and whatever, but what really sets it apart is it's excellent at math. And so there's a little sort of math language for typesetting mathematics that somehow, because it was designed by a mathematician / computer scientist, it's just really, once you get to know it, it's really nice and convenient, and it's a natural shorthand for writing mathematics with a keyboard. And it's now showing up in a bunch of different places that are not LaTeX. So for example, mathematics on the web now, most of it is MathJax, and MathJax is actually using the LaTeX markup for formulas. Newer versions of Microsoft Word, you can bypass this ridiculous equation editor that has you selecting things from drop-down menus and directly enter LaTeX mathematics into Word now. So the skills that there's a bit of a learning curve, but if you bother to do it now, it will probably come in useful in the future. Yep. I think there's a link on the course webpage to some resources, but there's literally like thousands of resources for learning LaTeX.
Yeah, but where it's on that tutorial, it gives us like an
Yeah, so if you, I don't know if I think there's actually some of the some of the material for this course is available on the course webpage as LaTeX sources. So taking one of those and working from that is a sort of good way to start. If not, go ahead and have a look and send me an email and say you said this, but it's not true. Then I'll put like an old solved assignment up. So that's a place to start. All right. So that's it for administrative details, unless somebody has a question at this point. Now we'll start on to give you a little taste of what's coming in this course. All right. So here's a not very precise statement. I'll call it a pseudo-theorem, because it's not really a theorem. And it says the following. Among any group of 6 people, there are always 3 who are mutual acquaintances, or 3 who are mutual strangers. Okay. So this looks something like a mathematical theorem, except there's a bunch of sort of things that we haven't defined. What exactly are people? We don't know what that is. But more importantly, what does it mean to be acquaintances, and what does it mean to be strangers? Okay. So underlying this, here's what we're going to say. So this is the underlying assumption, and there's a reason for choosing these words, acquaintances and strangers, is that every pair of people are either acquaintances, and I will just take that to mean they have been introduced to each other before, or strangers. They have never been introduced before. So take any pair of people, and there's a binary classification of them. They're either acquainted with each other because at some point in the past they exchanged their names, or they're strangers because that never happened in the past. So for example, in this class, most of you are strangers to me, and I'm a stranger to you, because we have never formally introduced ourselves to each other. So mostly the pairs of people that include me and one other person here, we would be strangers. There's a few of you that I am acquainted with because we have been introduced in the past, but mostly we're strangers. And actually in this group here, probably a good fraction of you, pairs of these people are strangers in this class. Pairs of students are strangers to each other, but there are some acquaintances. Some of you have been introduced before. The important thing is there's really only 2 categories. There's nothing in between. Okay. So this pseudo-theorem says, if I just take any 6 people, then from those 6 I can pick out 3 of them and 3 of them are complete strangers. Nobody amongst the 3 knows any of the others. Or the 3 of them are acquaintances, meaning each of the 3 has been introduced to the other 2. Okay. So is that clear? Yeah?
So if you take 3 strangers out of a hat, they could be, no, 3 people out of a hat, they could be strangers or acquaintances, or 2 of them could be acquaintances.
Well, what the theorem says is if you take 6 people, you can always find 3 that are acquainted, or you can find 3 that are strangers. Okay. So it's not any 3, because certainly you can pick 3 people where 2 of them know each other, but neither of them knows the 3rd one, for example. But in any group of 6, you can always find these things. And so this is it's now closer to a real theorem. And so we should maybe look at an example of what this is telling us. So here's 1, 2, 3, 4, 5, 6 people. And for any pair of people, we can classify them either as being acquainted or being strangers. So let's say I'll use red, and red means acquaintances. So for example, we can call these, well, we won't give them names yet, but you can see there's 6 disjoint circles here. Each one represents a person. So maybe this person is acquainted with that one, and with that one, and with that one. Maybe this person is acquainted with that one. I don't know, maybe this one. So there's a picture of what the acquaintances, the pairs of people who are acquainted look like. So each pair that's acquainted is represented by a red line segment. And our assumption is that every pair is either an acquaintance or a stranger. So let's draw the strangers. So this pair is not acquainted, therefore they're strangers. This pair is not acquainted, therefore they're strangers. This pair is not acquainted, therefore they're strangers. Strangers, 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 and 1, 2, 3, 4, strangers. Okay. I think that's everybody. Okay. So that's the picture we're looking at here. This is a particular group of 6 people and illustrating the relationships between them. So the theorem says, well, I should be able to find in this group, because it's supposed to be true for every group of 6 people, 3 who are acquaintances or 3 who are strangers. So what do 3 acquaintances look like? Well, 3 acquaintances would be 3 people who look like this. A red triangle in this picture. Is there a red triangle in this picture? Maybe I'll give them names now so someone can tell me if there's a red triangle. 1, 2, and 4, indeed, that is a red triangle. So for example, in this particular group, there are 3 mutual acquaintances and 3 mutual strangers is a purple triangle. Is there one of those in this picture? 6, 3, and 4, indeed. Purple, purple, purple. So actually, for this particular group, both of these things are true. But that's not what the theorem says is always the case. In this particular group, both are true, but sometimes you can only find one of these things. For example, if you take 6 strangers, nobody knows anybody, you're not going to find 3 mutual acquaintances inside that group. Or if you take a group of 6 friends who have been hanging out forever and they all know each other, you're not going to find 3 mutual strangers there. So this is a particularly nice example where you find both of them, but that doesn't always happen. Yeah?
6, 2, and 3, would that be a triangle of strangers?
6, 2, and 3, no, because 2 and 3 are acquainted with each other.
Oh, okay, sorry.
So that triangle is purple on 2 sides, but red on the other side.
Okay, what about 6? Oh, wait, yeah, sorry, never mind.
Yeah.
So, what's an example of strangers? Which one?
Strangers was 2, well, for example, 6, 2, and 5 is 3 strangers, right? 6, 2, 5, there's a purple triangle.
Okay, thank you, sir.
Good save. Okay, so, it's true for this example, but we want to prove that this is true no matter what the group looks like. So we have to do more than just draw an example. We want a general strategy for this, for proving this. So let's think about how we could find such a thing. So we're going to work towards a proof, first by doing an example, and then arguing that actually everything we did in the example will work in the general case. So let's take any vertex, person, I'll call this. Let's take any person, call this person A. So we'll focus on this one. And look at the segments coming out of A. So how many of them are there? So A is one of 6 people. So there are 5 segments, one going to each of the other 5 people. And each of those is either red or purple. So let's write down the steps that we're taking here. Let's go all the way over here. So pick any vertex A. There are 5 segments coming out of A. And now just to avoid awkwardness, does this picture, have you seen a picture like this before? Yeah, what is this? What do you guys call this thing in some previous course, like 1805? What kind of object is this? Yeah, it's a graph. The people, the circles, are the vertices of the graph, and the line segments joining those things are the edges of the graph. Okay. That's why I said vertex when I should have said person at some point, because I'm already thinking of this as a graph. And these line segments, they're the edges of the graph. So,
Those circles are vertices or vertex?
vertices is the plural of vertex. So let's just rewrite everything we're doing in terms of graph theory. And in this particular graph, if I look at any pair of vertices, there's an edge between them. Does that kind of graph have a name? Yeah, okay. So that's called the complete graph, and this is the complete graph on K on 6 vertices. So let's write it this way. Any 2 coloring of the edges of the complete of the 6 vertex complete graph contains a monochromatic 3 cycle. So this is just the graph theory version of this statement here. So I have a 6 vertex complete graph. So that means 6 vertices between any pair of them. There's an edge. 2 coloring of the edges means that for each edge I assign it one of 2 different colors. And monochromatic means 1 color. So I can always find, it says that in any of the coloring like this, I can always find a 3 cycle in which all 3 edges have the same color, either red or purple. So that's the mathematical, the really mathematical version of this pseudo-theorem. Okay. All right, so let's stop talking about segments. Edges. A is indeed a vertex, not a person anymore. So I have a vertex A with 5 edges coming out of it. Some of them are red, some of them are purple. In this example, what looks more interesting to me? What should I maybe think about focusing on if I'm looking at the edges coming out of A? Should it be the red ones or the purple ones? Well, to me it seems like since there's 1, 2, 3, 4 red edges coming out of A, if I'm looking for a 3 cycle that has all edges the same color, then probably I want to focus on the red ones. For example, I know already in this picture I can tell that I won't be able to find a purple 3 cycle that includes A because there's only 1 purple edge coming out of A and I would need at least 2 of them. Now in this case A has 4 edges of the same color coming out. Is that always going to be true? No? So how many edges of the same color can I be sure to find? Yeah. So there are 3 vertices. X, Y, and Z such that the edges AX, AY, and AZ all have the same color. For example, here's a vertex X, here's a vertex Y, and here is a vertex Z. AX is red, AY is red, and AZ is red. Now, why is that always going to be true? Well, if I look at the number of red edges coming out of A plus the number of purple edges coming out of A, well, that's all of the edges coming out of A, so there's 5 of them. All right, so if I have less than 3 red edges coming out of A, that means I have at most 2 of them, so then I must have at least 3 purple edges, right? And similarly, if I have more than 3 or more red edges coming out of A, well then there's 3 red edges coming out of A. That's enough. So that's actually an example of something we'll see more rigorously in this course. This is what's called the pigeonhole principle. Okay? So what happened here is 5 edges were split up into 2 groups. So one of the groups has size at least 3. In this case, the red group has size 4. Okay. All right, good. So let's look at that x, y, and z. So we've got xz, xy, yz. So that's a triangle, right? So what can you tell me about that triangle in this example? So purple, red, purple. So it's not the triangle we're looking for, but did you just see a triangle that we're looking for? So what do we know? All the edges coming out of A to X, Y, and Z are red. And when we looked at X, Y, and Z, we saw purple, red, purple. Do you see a triangle here, all of whose edges are the same color?
625.
Let's call it, no, not 625.
124.
Yeah, I want X, Y, and Z. So 1, so this is A, X, and Y. Now why did that happen? We had A, 3 edges of the same color coming out of it to X, Y, and Z. So stepping back away from this particular example, we know that right up until we really have this happening in every example now. And, well, we looked at X, Y, and Z, and what we found was that one of those 3 edges was red. In this case, it was the XY. Let's be consistent. In this case, the edge XY was red, which means we found a red triangle, right? Because coming out of A, everything is red. So as long as we could find 2 of these guys that have a red edge between them, we found the red triangle. It's the 2 guys with the red edge plus A. Okay, so let's write that down. If any of XY, YZ, or ZX has the same color, and let's be specific here. So there's 3 vertices such that the edge A of X, Y, Z has the same color. For now, we'll say red. And if any of these guys are red, then we have a red triangle. All right, so if any of these things, and that would be true no matter what, right? If XZ was the red edge, then that would be a red triangle. Or if YZ was the red edge, we'd find a red triangle there. So if there's any red edge between these 3 things, we're done. We found the red triangle that we're looking for. What's the other possibility? Yep. Yeah. So if there's no red edge between these three, that means all of these edges are not red, but there's only one other color, which is purple. So the only other thing that could have happened is this is purple, this is purple, and this is purple. And what did we find? There's a monochromatic 3 cycle. Okay. So otherwise, if we have a red triangle, otherwise x, y, y, z, and zx are all purple. So x, y, z is a purple triangle. Okay. And you see here, although we started working with an example, there's nothing that was said here that's not true about whatever we start with, right? So let's just back up and check that really carefully. So take any vertex A. Okay, all right, so that's easy. There are 5 edges coming out of A. Is that always true for every vertex? Yes, because it's a complete graph on 6 vertices. A is one of those 6 vertices, and there are edges going from A to each of the 5 other vertices. All right, the next statement is then, well, there are 3 vertices, x, y, and z, such that the edges AX, AY, and AZ all have the same color. Why is that true? Well, that's true because there's 2 different colors, red and purple. Red and purple together add up to 5, so they both can't be smaller than 3. In particular, they both can't be less than or equal to 2. So one of them is bigger than or equal to 3. And there's like something that should maybe set off an alarm here. I wrote, say red, but could also have been purple, right? So, and in this example here, I said, oh yeah, there's 3 red edges coming out of here, but they might have been 3 purple edges. So let's back up a little more and make this a little bit more precise and say, without loss of generality, assume AX, AY, and AZ are red. Okay. So without loss of generality, what does that mean? Well, you usually say it when there's a perfect symmetry between one thing and the other. So what I've determined is that coming out of A, there's 3 edges of the same color. Those 3 might be red, those 3 might be purple. But if I step back for a second and look at everything that's in the problem statement so far and everything we've done, there's no difference between red and purple, right? The theorem says, well, there's 2 colors, 2 different colors, and it says we can find a monochromatic 3 cycle. We don't care if it's a purple one, we don't care if it's a red one. So if I assume that these things are red, and I happen to find a monochromatic 3 cycle, the exact same argument should work if I assume that they're purple, but everywhere in that argument I'll have to exchange red for purple and purple for red. And if you don't trust that, if you don't really believe that that's a safe thing to do, then instead make a case distinction. So then if you want to really exhaust things, you would say, at this point, there are 3 vertices, x, y, and z, all have the same color. And you would say, case 1, AX, AY, and AZ are all red. Case 2, AX, AY, and AZ are all purple. And without loss of generality just says, somehow it means, well, actually, case 1 and case 2 are going to look exactly the same. But if you're concerned about that, if you ever have any concerns about whether an assumption is really true without loss of generality, just split it up into whatever, 2 or more cases. Okay. All right, so now we're working inside of case 1. And, well, now we can just put this argument in here. Case 1A, at least one of AX, XY, YZ, or ZX is red. In that case, we found a red triangle. And if you want to be really pedantic about it, you can break that into 3 cases. For example, case 1 is XY is red, case 2 is YZ is red, and case 3 is ZX is red. But I think you see that in any of those 3 cases, it's that red edge plus the plus A that gives it to you. Or you go to case 1B, which is none of them are red, therefore each of XY, YZ, ZX is purple. Then XY, YZ, ZX is a purple triangle. Okay. And in either of those 2 cases, we found a monochromatic triangle. And if you want to really complete the proof, now you have to move on to case 2, where the 3 edges coming out of A were purple. But you start to see what happens. Okay, the 3 edges coming out of A are purple. We would be very happy if we could find one more purple edge here. So then you get case 2A, one of XY, YZ, or ZX is purple. In which case we're also done. We have found a purple triangle if any of these 3 edges is purple. Or case 2B, each of XY, YZ, and ZX is red. And in that case, then XYZ is a red triangle. Okay. And if you really look at what happened here, case 2 is exactly what we did in case 1. We just swapped the roles of red and purple. So that's why it really was okay to assume that it was 3 red edges, because whatever argument we made to handle that, exactly the same thing works down here. Sometimes it's not always obvious, and some high-profile mistakes have been made in important things where somebody assumed something without loss of generality, which was not really without loss of generality. So if you're ever concerned about that, break it up into cases and deal with it that way. Often when you're doing the cases, you'll just end up with, basically copying and pasting a bunch of text. Then you can go back and say without loss of generality. Yeah.
I'm looking at possibilities because in case AX, AY, and AZ are purple, or in case they're all red, are you looking at possibilities? Are you doing it based on this one?
Yeah, I mean, you can think of, in this particular proof is very constructive. I mean, you could think of this thing as basically writing code to find this monochromatic triangle, right? The code is pick a vertex A, see what color comes out of A more often, red or purple. If it's red, then take 3 of those red vertices. You know, there's an if statement. If it's red, take the 3 vertices adjacent to those red edges. If it's purple, do this, case 2. But you could really write code for this, right? If you had a data structure represent.
Would you just add the different pairs in your statement?
Well, if I had 5 red edges coming out of A, just take any 3 of their endpoints.
But like, you update those statements to
No, because if you read this statement really carefully, it says there are 3 vertices x, y, and z such that the edge AX, AY, and AZ all have the same color. So that's true even if there's 2 more vertices, W and V, where that's true. But there's nothing. 5 red edges coming out of A does not contradict this statement. Indeed, it tells you that you could say something even more if you wanted, but we don't need to say anything more. And in fact, in this example, there were 4 of them, and we just took these 3 because they were my favorite 3. All right? Okay, so that's what a proof looks like. We went through this, very slowly here, but I think those of you who followed now are really convinced that this is true for any graph on 6 vertices. This statement is true. Okay. So any graph on 6 vertices which has been 2-colored, where the edges have been 2-colored. All right, and I'll just write down a third version of this theorem. Which is the following. Every graph on 6 vertices contains a clique of size 3 or contains an independent set of size 3. Okay, what does that mean? Well, this is a slightly different statement of the theorem because it says every graph, not a complete graph on 6 vertices. You can either find a clique or an independent set of size 3. So a clique is 3 vertices, all of whom are adjacent to each other. So that's what a clique looks like in a graph. And an independent set is 3 vertices, none of whom are adjacent to each other. So why is that the same statement as starting with the complete graph and 2 coloring the edges? Well, in an arbitrary graph, some of the vertices have an edge between them and some of them don't. So just think of it as, well, the strangers don't have an edge between them. So that's the picture there. And, all right, so a clique of size 3, that's 3 vertices that all have edges between them, so a cycle of size 3. Well, that's just 3 red edges, right? An independent set of size 3, that's in this graph here, those are 3 vertices with no edges between them. Well, back before, for example, that's, what did we say? This vertex, and nope, not that one. Where was the independent set, and where was the purple triangle before?
5, 6, 8.
2, 5, 6. Yeah. So there's an independent set, right? If I look at those three vertices, there's no edges between them. Why is there no edges between them now? Well, that's because there used to be purple edges between all of them before. So really, when you two-color the edges of the complete graph, that's like saying one color is used for the edges which are really in the graph, and the other color is used for edges that are not in the graph. So that kind of represents a two-coloring of the edges of a complete graph really means like any graph, basically. Okay. So there's another version of that theorem that's just about arbitrary graphs and talks about finding a clique, a bunch of people who know each other, or an independent set, a bunch of people who don't know each other. All right. Questions? Okay. So that's sort of one of the kinds of things that we will study here, and there are many generalizations of that. Where did the numbers 6 and 3 come from? Well, there's nothing special about them. You can ask this problem for any number. In particular, if I look in this room, there's like, I don't know, at least couple hundred people here, probably 300 people in this room. And without even knowing anything about the social network that is this room, I can be sure that I will find, I can be sure that I will find 5 of you, all of whom know each other or all of whom are mutual strangers, for example. So that's more than 3, right? Already with 6 people I can find 3. In this room, I'm certain I can find 5 of you, all of whom are strangers or all of whom are mutual acquaintances. So you can ask, replace 3 with any number here, and then ask what's the smallest number that guarantees to find a clique or independent set of that size. Very difficult problem. Okay, so here's something else we'll look at in this course. You may have seen this before. Quicksort algorithm sorts an array A of length n. And Quicksort is a recursive sorting algorithm that works as follows. If n is less than or equal to 1, just return A. So if I have an array and it only contains one value or it contains no values, then that's already sorted, right? There's nothing to do in terms of sorting. Sorting is really about making sure that the values increase as you walk through the array, but there's not even 2 values to compare in this case, so that's definitely sorted. Otherwise, pick a random value x from the array A. We got this big array A, or at least it's bigger than 1. We pick, just put our finger on some value here, arbitrarily. There it is, we'll call it x. And then we partition A into 3 parts. A minus, these are values less than x. A plus, values bigger than x. And A equals, values equal to x. And we're almost done. We return the results of quick sorting A with whatever the length of A is, plus all the values that are equal to x, concat plus all of the values that we get when we quicksort. All the values that are, so all the values smaller than x, all the values equal to x, all the values bigger than x. Okay. So what does that look like? We start with A, we pick a random value x from A. We do this partitioning, and in this partitioning, we get a little subarray, A equals, which contains all the values equal to x. Usually there's only one value that's equal to x in the whole array. We get a bunch of values that are all less than x, so these are all smaller than x, and we get a bunch of values that are all bigger than x. That's called A plus. So this is what happens when we partition. And then we recursively sort A minus, but now it's sorted. Then we take all the values equal to x, that's A equals. And we also, so this is quicksort A minus, this is quicksort A plus. Now we get A plus sorted. And we concatenate those three things, and that gives us our final sorted array. Everything smaller than x in sorted order, everything that's equal to x, and then everything that's bigger than x in sorted order. That's definitely an array that's in sorted order. Yeah?
So the beta parameter is on the bottom line.
Yeah, let's this should be length of A plus, and this should be length of A minus. So, for example, I encourage you to implement this in Python. The Python code is shorter than what I've written on the board here. Okay, so that's a sorting algorithm. And, well, you might ask, how fast is it? So I think we can kind of convince ourselves that it works correctly. Formally, if we wanted to do that, we would use induction on the length of A. That's the value of n here. And that's fine because the base case is when n is less than or equal to 1. We can agree that you don't have to do anything to sort an array of length less than or equal to 1. So it's correct in this case. And then, well, we do this partitioning. This is stuff smaller than x, equal to x, bigger than x. We apply induction here because this array is length less than n, so it's correctly sorted. This array is also less than n, so it's correctly sorted by induction. And then indeed, the way to get everything sorted is to have the stuff that's smaller than x in sorted order, then x, then the stuff that's bigger than x. So easy to prove that it's correct, but how fast is it? So what's the sort of weird thing here, the thing that we don't really have control over, is this particular step here. We pick a random value x from A, so we just pick something at random from A, and then we partition to get these three parts. What's the worst thing that could happen, or what looks like something really bad? Yep. Yeah. So if x is the smallest value in the array, right? Initially the array is not sorted, so even though we picked a random thing, that's not the first thing in the array, but it's anywhere, but we happen to hit the smallest one. Then we do our partitioning. And it looks like this. We have A plus. A minus is actually empty. There's nothing smaller than x. And here's A equals. So what just happened, we partitioned, we compared everything to X and did this partitioning. We recursively sort the empty array, but that's no problem. That's over and done with. But now we recursively sort this thing. And how long is that? So here we did n minus 1 comparisons. We'll focus just on how many comparisons this takes. And why did we do n minus 1 comparisons? Well, because we had to determine for each element whether it was bigger than or less than or equal to x, which means we compared it to x. So we did n minus 1 comparisons. Now, we're going to end up recursively sorting this thing. What's the worst thing that can happen? So we pick some random value here. We pick some random location. We look at the value that's in there. Let's call it x prime. And x prime is the smallest value in the remaining subarray. In which case we partition. X prime ends up here. Here's the A plus. This annoying thing still has length n minus 2 because it's only missing one of its values. And we did n minus 2 comparisons because we had to compare every element in here except x prime to x prime. So that's miserable. And this, I think you can see the pattern now. At the next stage, if we pick the smallest element again, we end up with this picture. We did n minus 3 comparisons. And this just goes on forever until eventually we get an array of length 2. We do 1 comparison to get down and finally to an array of length 1. And so if we add up how many comparisons we did, well, this was 1 comparison. Just before that, there were 2, then 3, then 4, and so on. So in the worst case, the number of comparisons done by Quicksort is 1 plus 2 plus 3 plus 4 all the way up to the n minus 1 comparisons that it did in the first stage, which is n times n minus 1 divided by 2, or if you like, that's n squared divided by 2 minus n divided by 2. Now, most of you haven't done too much study of algorithms yet, but this n squared is kind of not something you like to see when you look at the running time of an algorithm. The way I like to think of it is just consider what happens when n is 1,000,000. 1,000,000 is not a lot, right? I mean, that's if these were bytes, that's a megabyte, but if they're integers, that's 4 megabytes. That's nothing. That's not a lot of data. Well, if n is 1,000,000, then this n squared over 2, which is really the big part of this, is 500, 1, 2, 3, 1, 2, 3, 1, 2, 3. That's 500 with 9 zeros after it, so 500 billion. And I like to write things out this way because in a modern computer, the clock speed is measured in gigahertz, which is billions of cycles per second. And it's not a big number usually, right? 3, 4, 5. And instructions cost different amounts, but a few cycles per instruction is a common thing. So a good rule of thumb is this number of instructions, 1 billion instructions, takes about 1 second. So, like really roughly, would say this should take about 500 seconds. And 500 seconds is a lot of time to wait to sort 1 million elements. So in the worst case, Quicksort is not so good. But why is it called Quicksort then if it's so slow? Yeah? So the best case is n log n, agreed, but we don't usually care about the best case. Yeah? Yeah. So what we'll learn later in this course, and we'll analyze this rigorously, the average case, or the expected number of comparisons, is actually about n log n. So n log n. There's a constant here, but it's not a big one. And if n squared over 2 is about 500 billion, because n is a million, n log n is about 20 million. So it's not measured in the billions, it's measured in the millions. Here, n log n, 20 million. So how many seconds is that going to take? Well, this is not even a billion yet, right? To reach out to the billions, I even need another space here. So, if a rough estimate is that this takes 0.02 seconds. So, yeah, in the worst case, it takes about 500 seconds, but on average, it takes about 0.02 seconds. Big difference, and the only way you can know that is by, implementing it and trying it out, or just by through the analysis that we'll eventually do. So why is it the worst case doesn't happen? Well, it's because of this stage here. Right? We pick this random value x. It's not really that likely that every time we do this, we'll pick the smallest value in the array, right? I mean, that's sort of rare. If it's 1 million elements in the array, we pick one at random, we happen to hit the smallest value. That seems like a really unlikely thing. So the worst case essentially never happens, and the algorithm is indeed quick. So there's a teaser of the kind of stuff we'll be doing in this class. Where? Here?